we left off around break. I wanted to just do a little recap of loops. We'll start from break and continue, and then we'll go into lists from there. Okay, cool. Here we go. So this is sort of a continuation of the isPrime function here. We've talked about functions, and we've talked about various types up through lists. Let's do just a quick recap. Types, functions, conditions, loops. We're going to talk about while loops today, so we're going to cover our other primary kind of looping system. So the types that we've discussed: int, float, bool, string, none, and lists. I'm going to put lists on its own section because their lists are a little bit different. These types up here are scalar types, meaning that they're immutable. They don't have the ability to change value, whereas the list type is mutable, meaning its value can change while still being literally the same object in memory. Functions encapsulate a process. We've been over this. So one thing, and I fear that I may have forgotten to mention this, or maybe haven't mentioned this enough. So for this isPrime function, this isPrime function is being given as a Boolean flag controlled function, right? So we're starting this variable prime, we're setting it equal to true. And then throughout here, well, there's sort of a mix and match of what's going on because this is returning true. But throughout this, we're potentially setting prime to a different value and then returning prime after all of this is done. So something about functions that's worth noting: return will stop the function. So it'll stop in the middle of a loop. It'll stop. Yeah, it just stops executing code as soon as it encounters that return, right? Not during parsing, of course, but during execution. So when it's executing the code, if it encounters a return line, if it runs that executes a return line, no more code in that function is being executed for that, at least for that invocation. Conditions. Conditions are going to let us run code only when some condition is met, or more accurately, true. Loops repeat a process. And the process is just any arbitrary code. Cool. So that's how everything fits together. And let's take a look at this isPrime function. So taking off from the Boolean flags, I'm just going to copy this, and feel free to code along. IsPrime. We'll take in num. We'll start our flag equal to true. If num is, I'm going to say less than, if num is less than 2, we'll say prime equals false. And we'll say for I in range 2 to num plus, nope, not plus 1. I'm in the habit of doing plus 1. So 2 to num. If num I'm actually just going to call this n. I'm used to calling it n. Okay, so if n mod I, so if n over I has a remainder of 0, if n mod I equals 0, then I'll say prime equals false. There's another condition that tells us that prime should be false. And then after it's all said and done, we'll return prime. Cool. So I'm going to use a for loop actually to test this function. I want to test this on a variety of numbers. So I'll loop through and I'll get for I in range 15. This will get me 0 through 14, and yeah, we can go from there. So print I is prime I. Okay, so we'll see I, and then whether or not I is prime or not. Oops, and then of course I gotta execute my code here. Num is not defined. N, there we go. Okay, so 0 and 1 are not prime, so those are false. 2 and 3, etc., right? So we have our working as prime function. So using break, we can enhance this function a little bit. So you may recall I showed this last time. So if we currently, if at any point, for example, if n is equal to 9, we're going to check, we're going to start with 2, and we're going to see if 9 mod 2 has a remainder of 0, which it doesn't. Then we're going to move on to 3. If 9 mod 3 has a remainder of 0, which it does, then we're going to set prime to false, and then we're going to move on to 4, and we're going to keep checking numbers all the way up through 4, 5, 6, 7, 8. So we don't want to do that because we already know, like, we don't need to check any more numbers. We already know it's not a prime number. We found one divisor, and that's good enough to determine that it's not a prime number. So we can break the loop with break, like this. And what this is going to do is break bears on the loop. It applies specifically to the loop that it is immediately within. So yeah, so this is going to just stop. I mean, when you see break, you can read it as stop looping. Just stop the loop, right? And then we'll go straight into return. The thing is, we can shortcut the need for this Boolean flag, and we can just return false here, return false here, get rid of the flag, and return true here. So break is useful. I mean, there are uses for it, but to be honest with you, most of the time I'm breaking my loops with return if I'm using a break, because quite often you'll break and then you'll stop the loop and then go return something right after that. And if you do, you can probably just return the thing right there. So that's that. Can I clarify what I mean by shortcut? Is that something we should look out for? Ooh, I'm sorry, I don't remember when I said shortcut. Oh, sorry. Yeah, I do. When I'm saying, well, I don't want you to take away from this that like you have to do it a certain way. This way, I think, is objectively better. Like, there's no reason to do it the prime or the Boolean flag way. There's no reason to use a Boolean flag in this function. So to me, I look at that and I'm like, it's superfluous. It works though. So if you have a way of writing code that's maybe a little bit inefficient but works, then that's okay. Like if you know how to get things done, then it doesn't matter if you're doing them perfectly. It just matters that you're able to get them done. So yeah, the takeaway from this is that I want y'all to have is like return is sort of, its job is not explicitly to break a loop, but it's sort of a mega break, right? It's a de facto break to a loop because its job is to give a value to the function, right? Once the function evaluates to something, it doesn't make sense generally to continue executing code. There are sort of exceptions to that, although we're not going to cover that. If you're curious, you can look into generators in Python that use the yield keyword instead of return, but that's sort of a whole different can of worms. So when the interpreter encounters a return, it's just going to give a value back. So it doesn't make sense to continue executing code. So the function's over. So therefore, it's a de facto break on a loop. So the takeaway for this is that a lot of times you think you need break, but you can just use a return instead, because quite often you're thinking, okay, I want to stop looping because I've found what I'm looking for in this function that I'm writing, and then you'll return. And return only applies to functions. Like if you're doing this outside of a function, you can't have a return because return's only job is to say what a function returns. Okay, cool. Loops as filters. I want to kind of move quickly through this. Continue. So continue is kind of similar to break. Unfortunately, I think I need a different example here. Continue is kind of similar to break, but what it does is it skips one iteration. It just skips to the next iteration of the loop. So if I say for I in range 5, if I print, I'll just print I. And if I wanted to skip, let's say I wanted to skip the first 2 iterations, I could say if I is less than 2, continue. Right, and you'll see we're gonna skip the 0 and the 1. It'll just start at 2, 3, and 4. Right. So sometimes you do a process in the loop and there's a certain condition that if it's met, you just want to skip to the next loop. You just like, okay, I'll skip the code. So notice as soon as this continue line is run, it doesn't go finish the executing the code in the loop, right? It checks if I is less than 2, and if it is, it just continues on to the next loop. So you can read continue as a skip to the next iteration of the loop. Cool. Okay. Pass. Don't get it confused. Pass has nothing to do with break and continue. Pass is a placeholder. This might seem useless. Like, why would you have this? Trust me, it's very useful. If you're writing some code and you have like a if 10 less than 4 or something, I don't know. You have some condition, and obviously, 10 less than 4 is just false, but And you want to just provide a placeholder. This is good for like function heads. Too, if you have a function that you're going to write, so like def is prime, we'll take in n or whatever. So if I'm gonna write the is prime function or something, and then I'm gonna write def next prime, take in n pass, right? Pass is a great tool because it's valid code that just doesn't do anything. So the interpreter sees this and just ignores it and moves on to the next thing. And it's very useful for when you're just like putting up a scaffold or debugging or various other things. Cool. All right. Let's move on to, I think that's everything. Oops. Oh, we got Zoom asking me all the questions. I can't currently, okay. All right. Zoom. Sorry, let me just restart this screen share. Okay. Hopefully that'll work. Okay, cool. So let's move on to list methods and operations. So these are various list methods and operations. Various functions and tools that are built in. So some of these, I'm trying to see where it starts. Sorted, reversed, yeah. Okay. Some of these are functions and some of these are methods. We can see, so methods are built into the type itself. They are when you define the type, wherever the list object is, or the list class is defined in Python. The methods for that class are also defined as part of that class, right? So append, extend, remove, etc. So append is going to be useful. We can, oops, let me just, sorry, I'm still just fighting Zoom. Gosh. Append is going to be useful when we want to add things to the end of the list, which is, this is probably the method that we use most often. So the append method places a new value at the end of the list. And let's look at this. So if I have my list equals list, I can say list dot append hello. And then I can print my list. Cool. So my list now has the element that I passed to append to it, right? So this is how we can add things to lists and, yeah, grow them in size. This is what we'll use for list accumulation. You can see if I keep running appends, and if I ran this in a loop, right, I would append this more times, which would accumulate elements into the list. Let's look at this. Let's just run down all the methods for lists really quick. So I'll show you a trick there's a function built in called dir, dir, and you just pass it any data type in any form. So if I had list up here, I could just do that. But I could just pass it an empty list, and it will give me the directory for lists. And I'm just going to go down each of these methods. I said each of these. I'm going to skip the dunder methods up here. The dunders have a double underscore at the beginning and a double underscore at the end. So I'm going to do all the regular named methods really quick. What? Oh, that's insane. Okay, that's better. Okay. So dir will show you all the methods for a given type. And these are not the only tools used for processing that type, but that's a good chunk of them. And if you ever want to, a quick glance at what's available for a given type, you can use dir. So we looked at append. If I have list equals 99, oops, 44, and I list dot clear, that's going to clear the list. Oops. Let's prove that. And we don't need dir anymore. Copy is a useful one. So clear is just going to empty it out, as you can see there. Copy is a useful method to know. So this gets into what it means for a type to be mutable. If I look at this append example up here, if I print, I'm going to print the ID of the list. And we'll print the value of the list after it. And then we'll say list dot append 10, right? So we have an empty list and we're going to append to it. So notice that the ID for this list is the same in both cases. So it's the same object in memory. Even though the value is changed, it's not a different list that contains 10. It's the same list that contains 10. It's sort of like, the way I think about this is if you have a car and you take your car in to get a new paint job, if you have a red car and you get it painted black, it's still the same car. It just, you changed the value of its color, right? You changed what its color was, but it's still the same car. This is the same thing. We changed its value in some way, but it's still literally the same list. Count. So if I say list equals, let me just do this. 33. So count is kind of funny. So count doesn't alter the list in the same way that append does. Count is going to list dot count 33 is going to give me the number of times 33 shows up in the list, which is twice. And let's do this for 99 and 77. The 77 note is not in our list, obviously. So 33 appears twice, 99 appears once, and 77 appears 0 times in the list. So extend, you can think about extend is kind of like append, but its argument is another list. So if I say, I'll do this, list dot append. If I appended another list of, let's say, hello world, there we go. Oops. Dang it. Ugh. Okay. There we go. So if I append this list containing, so I'm appending, notice what I'm doing, right? I'm appending a list containing 2 strings to another list, which you can do. So I appended a list to another list, and now there's a list in my list, right? But if I just wanted to append every element in this list, I would have to extend instead of append. Right, so now my original list, LST, contains all of the elements from the list that I extended it with. Index, let's do this. So think about this. What index, let's say you want to know the index of 99. Go ahead and put it in Slack. What's the index of 99? I don't even need to really ask this. Yeah, there you go. There you go. 0, right? So list.index 99 will tell me the index of whatever element I pass to it. And this can be useful if you have like parallel lists and you want to know, which index something is at, so you can get the parallel item from another list. Oops. And again, index returns a value, right? Like count does, right? Index and count don't alter the list, they return a value. Okay, so that's at 0, right? So what if I do 33, index of 33? So what's this going to return? This is a little bit trickier because there's 2 33s in here, right? So does it return both in a tuple? Does it return the first one or the last one? And the answer is it returns the first one. It returns the instance of the first occurrence of the element passed as the argument. Cool. Insert is sort of like a extend and append, but it takes a second argument. So let's do list.insert. Insert hello, and its second argument is an index to pass it to. So right, if I want hello to be the element at the third index, 0, 1, 2, 3, it's going to displace this 33 and push that number to the right. Oops, sorry, I did the arguments backwards. First, it's the index, then it's the element. I do this like every time I try to use insert. I need to remember to print the list. Okay, cool. All right. So pop, now we've looked at several types or several methods that change the list, right? And several methods that don't. Oh shoot, I didn't really explain copy. I just like, I talked about IDs, but not actually looking at copy. Okay, sorry about that. I'll come back to that in a second here. So a few of these methods like append, extend, insert, and pop, remove, reverse, and sort. So these ones are going to alter the list in some way. Index and count are the only two that don't alter the list. They just return a value. Pop is weird because it alters the list and returns a value. So it's the only one that does both. And we'll get to that in a second. It's actually kind of a good time to talk about copy anyways. So the deal with copy, up here, I just showed the how using append, I could alter the list, but it's still the same list. So sometimes you might want to alter a list. You have an instance of a list that you want to make some change to, but you don't want to lose the original, or you don't want to corrupt the original or whatever. So you can copy the list in order to avoid that problem. So let's look at this. I'll demonstrate copy down here with pop, right? So let's say I have this list. I'll call this list one, right? So I want to pop, and pop as its argument takes an index. So I'll pop this 44 out. So it pops, it's going to remove whatever element is at that index and return it. Cool. So there's my 44 that I popped off. I'm printing it off. And then here's my list. So this alters my list. So let's say I didn't want to alter this. I could say list2 dot, or excuse me, list2 equals list1 dot copy. And that's going to copy my list to make sure I don't accidentally alter it, right? Oops, and I actually have to, let's print list2 here, and we'll pop from list2. And so we'll see what gets popped from list2, and then we'll see our original list is unaltered, and our new list is has that value removed. Cool. Okay. Remove is sort of like pop, but instead of taking an index, it takes an element. So let's do this list. Oops. So if I say list dot remove 33, so you can see it removes that first 33. So we end up with 99, 44, 33. And then I think we can do it. Can we tell it? Okay, yeah. Cool. Reverse and sort. So I think I'm gonna skip these because there are other tools that I think you're gonna give you an easier time for learning. It's not that there is no application for these, it's just that they can be a little funky and there are preferable tools. So let's pivot into functions. And I know we're gonna cover sorted and reversed. Yeah, this is gonna talk about that anyways. Okay. So let's pivot into functions. So we have the len function. So the functions are nice because they never alter your list. They leave your list alone. And you can count on the list having the same value. So len of this list. So this list contains 4 elements. Therefore, its quote, its length is 4. Just describes how many elements are in the list. Sum, and fortunately this is a list of numbers, sum takes in a list of numbers and, well, I mean, can you guess what it does? It gives you the sum of those numbers. Both are very useful. I find myself using len particularly quite a lot. Sum, not as much, but yeah. Good functions to know, especially len. Okay, sort and reverse versus sorted and reversed. So the sort and reversed methods are slightly different from the sorted and reversed functions. So remember how I was saying some of these let's see. We have a question here. Can you sum a tuple? Yeah, I believe you can. The thing you can't do here. Let's just make this a tuple real quick. The thing you can't do with a tuple is append to it. So actually, I was just gonna kind of talk about that. It's a good opportunity to talk about tuples. So len and sum work just the same with a tuple, and I just turned list into a tuple. So let's look at this. Append, copy, extend, insert, pop, remove, sort, and reverse all alter the value of the list in some way. Either they rearrange items, or they add in items, or they remove items, various operations that they do. Copy sort of leaves you a safety net against those things. It doesn't really it doesn't alter the list, but it makes a copy of the list. It makes a different list that has the same values in the same order, so that you can alter one without messing up the original or something. So it doesn't alter the list particularly, but it's only useful because the list can be altered. So tuples, the way that tuples differ is, imagine lists and then just take out all the methods that we covered that cause a change in the list. Other than that, tuples are the same. They don't have the ability to have operations that like change the tuple. So if you can concatenate tuples, which might look like a change, but actually what you're doing is producing another tuple from 2 tuples, and then you could reassign it or something. And we have another question. What happens if there are strings in the list and you sum it? Oh, let's find out. Let's find out, shall we? So let's say hello. Oh, well, actually, let's look at this. So Len's going to work fine. Excuse me. Oof. It's sitting kind of weird or something. Type error, unsupported operand types for plus int and string, right? So if I pass, let me do this. Oh no. Shot myself up to the top of the document. Okay. So if I do this list in here, this is going to give me a type error. So sum, and this is a good example about the types of, or the valid ways we can think about inputs, right? So we can think about an input has to be a certain type, but there may be other constraints on the input, right? Like, I don't know, I mean, just off the top of my head, maybe I would write a function that would take in a string, but the string has to be longer than 3 characters and less than 16, right? I could write a function that has that constraint on the input. Sum has a constraint, which is that all of the elements in the list have to be summable, right? They have to be able to be summed. You have to be able to add them all together. I am just curious because I know we can use concatenation. I'm curious if I have all strings, if it will concatenate all the strings together. Pretty sure I've done this before, but we'll see. Nah. It still wants it to be an integer, so okay. That'd be funny if you could use sum that way, but actually that's better that you can't, right? That it's constrained to only doing the job that you think it should do. That's a better thing to do. Okay, cool. So sort and reverse versus sorted and reversed. So sort and reverse are functions, or excuse me, are methods. They cause a change in the list. They one sorts the list, and the other reverses it. I'm going to point you at the sorted and reversed functions because rather than altering the list, they give back values, and that can be helpful. We got another question here. Sorry, I missed some questions. Sorry, folks. Does sum work on any other types besides lists? Yeah, so in any, I think it'll work on generators. Yep, it'll work on generators. And tuples and lists. Yeah, just so long as all that it sees is numbers inside a collection. It doesn't matter what the collection is, right? So if we had a range, I think we could sum, let's do this. Print sum range. So range is technically its own type, but it's something, it's kind of a special thing that we call a generator. I mean, you've seen me do this, print range 10. Try that out and you'll just see it just says range. I believe what it does is just print range 0, 10 like this. But when we iterate through a range, it acts very much like a list of sequential numbers. So what it does is under the hood, it sort of maps to the next iteration without doing that all at once like a list does. So we could sum a range, like if I wanted to sum the range 3 to 17 or something. I think this will sum every number in that range. Yeah, so every number between 3 and 3 plus 4 plus 5 up to 16 is 133. So yeah, as long as it's a collection of numbers, sum will work. That's a good question. And then what is a use case for tuples over lists? Good question. I generally, I will generally, like in class and in the coding that I do in public, I'll default to lists, but just because I want to get people practicing them because they have a little bit more moving parts. In my own coding, I'll generally default to tuples, though. The use case, it's kind of funny, right? Because you might think, well, okay, so tuples are just like, they're just like kind of weaker, less cool lists. If you're going to have a collection of objects, like, why not make it as capable of doing a variety of things as possible? Why not give it as many tools as possible? And, that's a fair enough assertion. The thing is mutability is a powerful feature, and it's necessary. Well, I think some would argue with me on that, but I would say it's, for our intents and purposes, it's necessary. But you sort of, it's a trade-off. There's a bit of a trade-off. When you have a type that can be mutated, a mutable type, when you have a mutable type, you sacrifice to some degree some level of being able to predict, well, particularly the size of that type. If I have a tuple in my memory, I can alter the pointer. There's ways of altering the pointer that that will look a lot like an insert or an extend or an append. There are other ways of doing that with tuples, but they're so explicit that, like, something, if you alter the size of that tuple, it's not happening without your knowledge. The worry with a mutable type is that, let's say you use some third-party library that seems pretty cool. Maybe it's in beta, or maybe it's just a small project that's just not well developed in some ways, or they have a really different paradigm about what good coding practices are, or it's no longer maintained or whatever. Like, there's a variety of reasons that a body of code might do this, but you implement some function from some third-party library that seems to do something that you want it to do, or maybe somebody on your team writes some code that does this, although hopefully nobody writes code that does this. They write a function that takes in a list and alters the list that it takes in. Let me show you. So here's my list, and what should it be? Hello world. And for whatever reason, there's a function that you end up using that's takes in a list and says list dot append takes in a list and an object, and it just appends it. Okay. And we'll say hi or something, I don't know. So we know what to expect this to return, right? It takes in a list and an object, appends the object to the list, and returns the list. Not a big deal. Well, if it ever runs, God, it's like it's getting slower and slower every day. Okay, so the question is, what's the value of my list? So my list was altered by this function, right? So code like this is out there. It does exist. It shouldn't exist. I'm I apologize because that is my opinion, but I'm right and I'm sticking to it. Code like this, functions should never mutate their inputs. You might be able to convince me that there's some circumstance where an exception should be made to that. Maybe there's a scenario where an exception should be made to that. But if an exception ever were made to that, I would put like mutate or like mutable like in the name of the function. This is what I would do myself. To make it very clear that it does something that it probably shouldn't do. But this is sort of the worry with lists, right? So you have, it's hard to see in just this small example, but imagine that this code is in a library, right? And it's function 493 in a document with 15,000 lines of code in it in the middle of somewhere, and you implement it somewhere in your code, and this isn't just some stupid list with a couple strings in it, it's like your data, right? Well, you just passed your data into the thing and it got messed up. Tuples don't do that. So if this is a tuple, granted I have to rewrite this function in some way. Right? So if this is a tuple, I'm sort of safe with that. Tuples don't have the ability to be mutated in the same way, right? Now, you don't have to go rewriting your code and custom tailoring everything because you think in like immutable terms and you like to use tuples like I do. You can do list equals list dot copy, and you can still use a list, right? So we've made this dangerous function safe, and this is okay. Right, so there are ways of using lists that are safe, but it's like you kind of can't count on it. There will come a point where you're worried, like, what if something happens to this list? What if, and it's not going to be like it's rare that you'd actually like corrupt something that you need. It's more like your program's memory is just not going to do what you wanted it to do. But yeah. Anyways, this is quite the rabbit hole, and I fear I've already dove deeper than I should have, but that's a good question. Somebody's asking, are there vector types? I'm familiar with vectors in Rust being like typed lists. I don't believe Python has a built-in typed list. There are third-party libraries that do have typed lists, though. And I'm not sure if they're called vectors or whatever, but I'm not sure if that's canonically what a vector is in other languages. I think that's the case, but yeah. Yeah, sure thing. I think to answer your question, like the short answer is lists are Python's vector type, except that they're never constrained to whatever kind of type. You just have to make sure you only add in valid things in. Okay, cool. Sorted and reversed. Okay, we took a couple of questions there. Sorted and reversed. Let's get back on topic. So it's common that you might want to, let's do this, list equals, I'll just do some random data. Okay, so it's common that you want to sort things in your list. It's actually more common than you might think. You might think, oh, well, that's a very particular thing that maybe I'll need that someday. You'll definitely need this. It can be very useful to order your data in some way relative to the values within the list. If you sort strings, I think sorted can take in any type, but it all has to be the same type. I don't believe, like, if I have a string in here, I think this is going to give me an error. Yep, greater less than operator not supported between type instance of string and int. So it doesn't know how to sort a string with an int, which I mean is fair. I don't know how to do that either. So you can sort a list of strings. You can even sort a string and you'll get a list back. It will, if you sort strings, it'll sort alphabetically, quote unquote. The actual ordering that it uses is called lexicographical order, which is like a superset of alphabetical. It's special characters first, then capital ASCII characters, lowercase ASCII characters, special characters, then numbers, then uppercase, then lowercase. So it's like a superset of alphabetical. I believe that's the ordering. I might be wrong. You might have to check on that. You could play around with it and check that out. Can you sort numerical values and Bool? Let's try to do that. Let's throw a false in there, see where it puts it, or if it gets us an error. Looks like it puts the false at the beginning. So, I mean, Booleans are a numerical type, technically. So it looks like it puts it at the beginning either way. I'm assuming it's going to put false before true, but I don't know. Yeah, it does. So it looks like you can put bools with your numbers. And if there were floats in here, it would, I mean, hopefully that's obvious. It would work exactly the same. Cool. So that's sorted. So nice thing about this kind of gets back to that that tangent that I went on with that question. And you'll see this in my, and this is a personal choice in my own particular coding. I favor things that don't I don't avoid altering, I don't avoid mutation at all costs. Like there are coding paradigms where like you never mutate, you never ever cause a mutation in a type. You treat everything as always immutable, and those are, it's really cool. It's cool to think that way. It's fun. In practice, I don't care that much. So I mean, mutation is useful, but I lean into not doing it by default. If I have a choice, if I can get away without mutating something, then I'm gonna probably do that. So this is why I prefer the sorted function. If we look at these, here I have the sorted list, and here I have the unsorted original list, right? If I wanted the pointer to point at the sorted list, I could say list equals sorted list. Technically, I'm adding a little bit of memory overhead to this, but I don't know. It's easy. So this will alter the list that the pointer points at, that the identifier points at. But it doesn't actually alter the list, right? So I could do something like, OG list equals list dot copy if I wanted to keep that around, something like that. But yeah. Reversed, I'll just reuse this code. Reversed doesn't probably do what you think it's going to do. So when I print reverse, so notice the second list being printed out, so it doesn't alter our list. So we'll just establish that this doesn't cause a mutation. So reversed returns a list reversed iterator object at blah, blah, blah. It gives us a location, a memory location here. So if I wanted to use this as a list, I have to cast this as a list. The reason it doesn't give you a list back is, you already have a list here. So what it does is it just maps a reverse iterator object over the list so that you can iterate over the list backwards. And there's times where you want to do that. There's times when you want to iterate through something from right to left instead of left to right. So the use case here is more for like for I and reversed list print I, and you'll see we'll have 11, 33, 99, 22, 77. Maybe I could do both, right? I could do sorted. I could do that. But sorted, if you're going to sort and reversed, sorted has an interesting thing you can do. You can pass what's called a keyword argument. Reverse equals true. And I don't remember if it's reverse or reversed, so this might give me an error. No, it is reverse. Yeah, so reverse equals true. So notice we get 99, 77, 44, etc. If I change this to reverse equals false, then we'll get 11, 22, 33, etc. So with this, we can sort in ascending or descending order with this reverse flag by setting it to true or false, which is pretty handy. Okay. Min and max. Min and max are pretty straightforward. These will actually work. These will actually work on a list of strings. I would say, well, I think some of our material will get into that. It'll work on a list of strings, but the behavior is a little bit unexpected. I believe it goes by like the sum of the ASCII values. So the behavior is a little bit unpredictable. It feels a little weird. So mostly just use min and max with lists of numbers. It will work with other things, but lists of numbers is sort of what's predictable and easy, and that's sort of the I would argue the primary use case here. Any and all. Let's move on to any and all. So remember we talked about this idea of truthiness and falsiness. It's and there are different schools of thought on this, which is fine. In my opinion and experience, and there could be a reason that I'm objectively wrong about this, but I tend to see truthiness and falsiness as a little bit of a sort of like, but why does this exist? You know, like I tend to prefer systems that like maybe add more constraints, but make things clearer. I find that makes code more consistent and more clear. But yeah, so any and all is sort of tied in with this idea of truthiness and falsiness, and we can. It's basically going to say if any of the elements in a list are truthy, then any will return true, right? So all of these are truthy, so this is going to return true. So our falsy values list equals, let's just put some falsy values. Falsy values are going to be, empty string, empty list, empty tuple, 0, 0.0, etc. Right? So any is still going to return true because I've got, or why don't I just constrain this down to just one truthy type or one truthy value. So that's still going to be true. All is going to be false because all only returns true if all of the values are truthy. Right? So if I gave this list to all, then that would be true. And then, of course, if I delete any truthy values from the list and pass it to any, that's going to be false because all of these values, 0.0, 0, empty tuple, empty list, empty string, these are all falsy values. Cool. We're running light on time. I apologize, but I'm gonna skip the breakouts. Enumerate. Let's get into enumerate. So here's one of the most useful functions that you'll encounter for loops and lists. Let's say I have my list of numbers. I'll use this list of numbers here. And let's say I want to raise every number to the value of its index. And there's a lot of things in math that are like this, where you want to actually use the element's position in the collection in your formula. So you'll see this a lot in math. So let's see. So if I say for IDX element in enumerate list, right? So notice how enumerate changed. Oops, I got an extra comma in there. It changed the way we write our for loop a little bit. Let's do this. Who remembers here? I'm going to use pass because I'm going to come back to this, right? So who remembers what we were talking about with A, B equals 3, 4. We mentioned this near the beginning of class. So if you just comma separate values like this, it's actually a tuple. And you can deconstruct those. If any place where you can give identifiers to those values, you can unpack them like this, right? So this is called unpacking. Yep. Yeah, and it's a way of assigning multiple values at the same time. So anytime you have a tuple, this is another argument for tuples. Like if you're going to be unpacking things, you need to know that you know, like you need to know in your code, I'm unpacking 3 things or 2 things or 5 things. How, you know, like you need to know what that number is, and you need a guarantee that it's going to be the same number of items every time. A list does not have a guarantee about what size it is. You know, something could come along and change the size of a list, but something can't do that to a tuple. So, you know, this is kind of the another argument for using tuples. So enumerate actually gives us a tuple back containing the index and the element in the list. And let's actually just look at this. Print type tup, which is going to be a tuple, and we'll just print tup next to it. So class tuple, and then you can see it's a tuple containing the index. If you look at the left-hand numbers in these tuples, this is a little bit confusing. Let me just delete that. If you look at the left-hand numbers, you'll see 0, 1, 2, 3, 4, 5. Those are the indices. And then the right-hand numbers are going to be the elements in order, 44, 77, 22, 99, 33, and 11 from left to right. So it gives me access to the index. And usually what we do is we unpack it right here, IDX, ELE for, I'm just going to call it, or let's do num. These are all nums. IDX and num. Bingo. Nice and easy. So that just unpacks it into their own variables, right? So let's say I want to like raise each number to the power of its index. I can do something like this. Cool. Parallel lists. Unpacking nested lists. Okay, let's talk about parallel lists really quick. So parallel lists, if I do this, names equals, I was just going over this in Learn today. Let's say Jane, Joe, Jesse, and ages is going to be, let's say, 32, 57, and 98. And I want to print out each person's name and their age, right? So the first element in each list corresponds with the first element in the other list, right? So Jane is 32, Joe is 57, and Jesse is 98. So I could print an F string, right? F, something like name is age years old. But I need name and age. So one thing I can do is I can say for I in range, and just pick one of these, use the len, the length of the list, and say ages. And then I can recuperate these variables like this. I can say name equals names sub I. age equals ages sub I. Okay, cool. So I could do this, but fortunately there's a much more elegant way of doing this. Similar to enumerate, this approach is going to give me a tuple back every time, so I can unpack that tuple in line. I can do, let's do name and age. So for name and age in zip names ages. And then I don't need these variables. And I can just pare this down to a couple simple lines. So if you ever find yourself saying, well, I need to iterate through 2 lists at the same time, zip is the tool. Unpacking nested lists. I'm going to skip that part because it's, I don't know, it's sort of, it's there, you can do it, but it's honestly just won't come up that much. Cool. Let's get into while loops. Hoping we'll have enough time to get through at least while loops. I think I'll have to push strings off to the next day. Okay. So while loops, we've talked about I'm going to explain this by sort of talking about 2 things that we've already talked about. While loops can be thought of as somewhat of a combination, right? So while loops categorically belong with for loops. So we have for loops, which are a type of loop, and while loops, which are another type of loop. Sometimes while loops are called conditional loops. We've talked about conditions, right? So conditions execute code while something is true or when something is true. So an if will say, excuse me, gosh. How should I do this? You know, let's give this context. I'm going to do the isPrime function. I'm just going to try to hammer it out really quick, see if you can race me. My typing skills are not that fast, so you might be able to outdo me if your logic is good. So if n is less than 2, return false for I in range 2 to n if n mod I equals 0. Nice, somebody beat me to it. If n mod I equals 0, return false, return true. Okay. So I'm hoping this function makes sense. It's not terribly complicated. It's got a little bit going on, a little bit of everything going on. We've got 2 conditions. We've got a for loop, loop through a range, and we've got a few returns in here as well. Here, I'll put this back on the other line. So how's this condition work? It says, well, it's going to check if this is true or false. This expression can give me back true or false. If it's true, it's going to run the code inside. So if n is less than 2, n less than 2 is true, it's going to return false, right? Otherwise, it's not going to do anything. It's just going to move on, right? So a while loop, think about it similar to an if, except it's going to loop while the condition is true, which means that something in the condition has to change in the loop. Otherwise, the condition is going to be true forever, and then you're going to have an infinite loop. So we want to avoid infinite loops. And for loops are nice because, look at this, for I in range 2 to n. it's just going to go, like, the boundary on this is already set. And this is the case for for loops. When the boundary of the iteration is known, or another way of saying that is when you can determine how many iterations are necessary before the first iteration, you can use a for loop. If you can't do that, and there are situations, we'll look at one related, fortunately related, conveniently related to the isPrime function. There are times where you can't determine, it's impossible to determine how many iterations will be necessary to complete a task. Or the process of determining it is just literally completing the task. Okay, so def next prime. So next prime is going to take in a number and return the next prime number after that. So if the number it takes in, if n is itself a prime number, it's not going to return n. So if I pass it 7, I don't want to return 7. I want to return 11. Yeah, 11. So let's make some tests for this. and let's think about this. Who can tell me why we need a for, or why we need a while loop for this? You can give me the gist. Let's see. We don't know how many iterations are needed. The number is unknown distance away. Yep. Because we don't know how many of these will be. Test the condition. You don't know how many iterations to get to the next prime. Yep, the amount is unknown. Yep, good. So the prime numbers are what they call an irrational series. The distances between primes is just fundamentally not predictable. There's not a pattern that has ever been able to be discerned. I believe that they've proven that no pattern is possible or findable. No pattern will ever be discovered. I believe that they've determined that as well. So therefore, we need a while loop. So what I can do is I'm actually going to reappropriate the n the parameter here, although you could just as easily do something like counter equals n. So the way to find the next prime number, like I said, I'm just going to use n, is we want to iterate while not is prime n. Okay, so here's my condition. So while this is like saying, it's a little bit convoluted in English, while not is prime n, to you and I might read better as while n is not prime, but given the limits of the language, this is as close as we can get. So while n is not prime, and I think, do I want to do n plus 1? Well, n plus 1 is not prime. N plus equals 1. We're going to add 1 to n. And if we don't do this, notice n is my variable, right? It's the thing that can change, that can control whether this loop is going to loop forever or not, right? So n plus equals 1, we're going to just add 1 to n. And then when this is false, that is when is prime is true, This returns true, not true is false. Then while false just stops, and we'll return. And I think we need to do n+1. This solution feels a little unnatural to me. I'm trying to do it the conventional way. I'll show you the way I prefer in a second here, but okay, no, this does work. Yes. Okay. So, we get starting at 7, we get 11 all the way up till 11, then we get 13. Good. So this does actually work. Cool. So here's what I prefer to do. Well, let me write it like this. Okay. So what I prefer to do is while true. Now this is kind of an unorthodox thing. Full warning here. I think people will look at this and think it's not best practice. I don't know that it says anywhere that it's not best practice or that you shouldn't do this. The control of this loop is not in the loop head, as is convention. The control of this loop happens in this condition, right? So this might be a case for break. Oops, and I actually just want to do n here, not n+1. Right? You might say, you might break instead, right? In this case, I can and do prefer to just return as a default break. So when you write a while true, what you're saying is just loop until I tell you to stop. And this is actually, I really like writing loops this way. It's boneheaded and it's simple, and it makes a lot of sense. I think it's a really easy way to think about while loops. Just write in while true, and then have a condition somewhere that causes a stop, either run break, or quite often, like I said, quite often at the end of your loop, the next thing you do is return. So in this kind of structure, often you can just use return to just break the loop. So the way this reads, so while true, just this means loop forever. N plus equals 1. If n is prime, then just return n. Nice and easy. This solution to me, just like the paradigm of explaining it, reading through it, is just much easier, I think. And I, you're free to disagree. Your brain may well work different than mine, right? But while not is prime n+1, add 1 to n, and then return n+1. I can read this code. I know what it does, but I do find it harder to think about. In my own code, this is, I think, always what I do at this point. I actually discovered this kind of looping. It's actually in Rust. Rust has a loop structure called loop, and it loops forever. It just loops until you run break in it. And Rust has a break keyword as well. It's called break. I mean, it's exactly the same. So it just loops forever. And at first I saw it and I was like, why would anybody do this? This is insane. And I started using it and I was like, oh, this is like a while loop, but it's so much easier to deal with. And so I just started writing my while loops this way. So yeah, so I recommend this way. Just start with a while true and make sure you have a condition somewhere that tells you when to stop looping. The conventional way is to control the loop in the head like this, but this is a little meh. we got a few questions here. Or just one, it looks like. Could you do another example of conditional while loops? Well, while loops are, while loops are conditional. These are conditionally controlled in either case, right? The idea with conditional is that the rather than stopping the loop or controlling the loop based on the end of some predefined series, you stop once some condition is met. So paradigmatically, these are the same, right? We have the same paradigm. This says we stop looping once the condition in this loop head is met. This says we stop looping once the condition in this if statement is met. So yeah, either way, it's a conditional controlled loop. I think what you mean is another conventional while loop. Yes, we can look at that as well. I do want to just give this as an example because I find it much. I find that people struggle a lot with while loops, and I think big part of it is it's really unnatural to think of what's the condition that tells you you don't have what you're looking for yet versus what's the condition that tells you you have what you're looking for. It's really easy to think about I found what I'm looking for versus I haven't found what I'm looking for yet. A lot of times you can think I've found what I'm looking for and just throw a not in front of it, and that'll work for while loops. But yeah, I find a lot of people tripping up on while loops for this particular reason, and I find that this is a good antidote to that. But that being said, learning how to do it both ways is really the right thing to do. Okay, so let's just look at this. Let's look at this again. So let's look at a really simple while loop. So let's say while, and it's convention to call this I equals 0, and we'll just do a simple counter. While I is less than 10, so again, if I is less than 10, this makes sense, right? So while I is less than 10, print I. Who sees the problem with my code? What's going to happen? Yep, there you go. Yep, we're just going to print 0 forever, and let's just go for it. Let's try to break my my work computer. Oh, did I say that? There we go. It's just printing zeros forever. Oops. Oof. It's really slowing it down. Okay. I had to stop it manually. Okay. So I have to say I plus equals 1 every time. So this does actually give me a huge amount of control here. Whether I'm controlling it here or if I'm doing, oops. Sorry, it's still in infinite loop mode. Oh my gosh. Okay, there we go. So this is going to print out 1 through 10 here. Yeah, so usually what I like to do, just to keep everything organized, is to do your incrementation first thing in the loop. Quite often, though, you'll be tempted to start something at 0, and increment until you reach some boundary. But often you'll want to use the element as an index in something. So if you start at 0 and the first thing you do is add something to it, you've skipped index 0. So often you might end up wanting to start at -1 so that your first incrementation gets you to 0 and you can use it as an index in something. So that can be kind of a juggle to figure out. But yeah, just as a tip, just keep it all together like this on these 3 lines. Initialize your controller, put up your loop head, and then your incrementation of that controller, your alteration of the controller. And then whatever process you're going to do in your loop. So that's the thing to do. Okay, so using for in place of a while loop. So a for loop can be set with an arbitrarily high ranged number and an escape condition. So this is a pretty straightforward while loop, and most while loops that you're going to write are going to just have a simple, like, sort of incremental control like this, where we're controlling the exit based on just incrementing I by 1 until some threshold is met, right? If this were like 10,000, I might want to, for testing purposes, I might want to do something like if I is, or let's do something even more drastic, 100,000, a million. We'll do a million. Okay. Right. So I might want to say, like, if I is greater than 1,000, break. Just for, like, development purposes, make sure my logic is good. Like, while I'm getting everything together, this is sort of an emergency stop or an emergency break, just to make sure we don't end up doing a million loops if we don't want to. Then I can just comment that line out and test it for realsies. We'll see. This is going to go for a little bit. We're up to 80,000, 90,000, 100,000, etc., etc. Cool. So just like having some ideas built in on, like, how to break your loop in case it gets into an infinite loop. Conversely, here's an example of, like, if you don't know how many iterations it's going to take to do something, but, like, if it takes you, what is this, 10 million? If it takes you 10 million, you're just like, okay, it shouldn't have taken me this many. Sometimes there can be, like, sort of an implicit or subjective upper boundary where you're like, well, given the application of this particular function, I know I'm never going to exceed whatever boundary. You can sort of cheat and use a for loop instead of a while loop in this case. There are some problems in Learn that you can cheese this way, and it's sort of, you're sort of getting by without really writing the for loop that you should have wrote. But if you're comfortable with for loops, you can get by like this. It's a way to make something work like a while loop, even though it's still a for loop. So conditional while loops. Okay. Mostly while loops get initialized with some sort of condition statement. The while loop will execute the code within it until the statement is no longer true, until the statement is false. Okay. Open-ended problems. Sometimes we'll use this term open-ended problems. That just describes a problem where we don't know the number of iterations necessary to solve the problem. Another example of this, let's say you're writing a menu, or like you have a game and you want to ask the player if they want to, like they end the game or the game ends, and you ask the player if they want to have another game or something. And if they put in yes, then you have another game, and if they put in no, then you quit, right? So um, while loops are often used in conjunction with the input function, the input function, um, for this reason, right? They sort of balance each other. Um, let's say list equals empty list, and let's just say we could say list dot append. We could do something like it's going to append the result of input. Please enter a name. Let's say enter a name. And then we could ask the user if input, do you want to enter another name? Yes or no. So if this input equals no, let's do this. If that equals n, then we'll break, right? So if I run this, I enter name. Do you want to enter another name? Yes. Enter a name. Yes. Yes. Enter another name. And then we can say no. And then that'll stop our function, right? And if I had remembered to print list, then we would have seen the list populated with all the names that I entered there, right? So this is a really simple kind of menu system. It obviously doesn't do anything that useful, but yeah, it's a good example of like how we can use input perhaps to collect records from a user, append them into a list, and then check an input, prompt the user to ask if they want to do the process again or whatever, ask them what they want to do. And depending on their input, we can just end the program and break the loop. So a lot of programs are structured this way, larger programs, applications, with a main loop under the hood. There's your while loop right there. So, and I suppose if we wanted to control this in the conventional way, what would we do? We would do this up here. Something like that. I don't know. Anyways, I think you get my point. Okay. Menus. Yeah, so this is basically talking about what I was just talking about. So this looks like a like a restaurant ordering menu. We've got selections, and then add another order equals true, right? So while another order equals true, this equals true could just be taken off. So while another order, this is going to print off the menu string to tell the user what the menu items are. And then we'll ask for input, cast it as an int. Please make a selection 1 through 4. 1 is bread, butter, potatoes, broccoli, etc. And then if input in 1, 2, 3, 4, so this is input validation, making sure that the input is actually valid, then selections dot append input, right? So that's going to append whatever the input is. Else, print your input selection was not understood. And then continue is going to send you back up to the top of the loop. So that just ends this iteration and we go back up to the top of the loop. And then the second input, the second input's actually going to control our loop, right? So would you like to place another order? If imp equals y, then we just continue. Else another order equals false, then we come back up to the top in either case, and false is not equal to true, so we stop the loop. So for versus while loops. So while loops are capable of solving, I went over this in the beginning, but while loops, just to be clear, are capable of solving any problem that a for loop can solve, plus more, plus other open-ended problems that a for loop isn't really well suited for solving. That being said, for loops are just way easier to deal with. They make more elegant, more succinct, more readable, more writable code that's generally robust against getting into infinite loops. There is a way, I think I mentioned this before, but I believe I've seen in more than a year and a half of, well, more than 2 years of doing this job, I believe I've seen one person write a for loop and get it into an infinite loop on accident. You generally have to you generally have to go out of your way and do it on purpose to get a for loop into an infinite loop. That being said, if it happens to you, then don't feel bad. Think of it as an achievement, right? Like, how would you write an infinite for loop? There's a couple of different ways to do it, but they're pretty weird, and they're generally not code that you're going to write on accident. So yeah, for loops are easier to use and they just make for cleaner, more readable code. So I would say most of the time you can get away with using a for loop. Whenever you can, definitely do it. So, all right, it looks like we've just got, is this just breakouts for the rest of this? Cool. Yeah. So let's do a couple of these breakouts. Well, or should we get onto strings? We're not going to have time to get all the way through strings. I'm gonna have to roll in strings into the next lesson because this is a type that's it's a pretty central type. It's simple, but it's also very central, so it's worth taking the time to do that. As for the breakouts, I'm just gonna roll the breakouts into part of homework for y'all, and we can just wrap up a little early today. I think that's fine. So yeah. We'll just let me stop the recording and we can take questions.